All right, so let's talk about series. A series is when you have a sequence and you add up the terms. Add up all of them, some of them, that's all called a series. So in pre-calc, you probably dealt with finite series where you just added up some of the terms, right? There's even some formulas for that, like an arithmetic series. You can do what, a1 plus an times n over 2, right? We're not going to do that. We're basically going to talk about infinite series. Infinite series are tricky. It's hard to add up an infinite series because there's an infinite number of terms, so how do you add them all up? Don't you get tired? Don't you run out of steam? You're never going to finish. How do you know what the sum is if you can never finish adding up all the numbers? This is very confusing, okay, and distresses people. So we're going to make a rule for this, and what we're going to do is we're going to consider something called partial sums, and we'll look at what their trend is. So partial sums is when you add up part of the series. So the first partial sum is the first term. The second partial sum is the sum of the first two terms. The third partial sum is the sum of the first three terms. The nth partial sum is the sum of the first n terms. And when we want to say, does an infinite series converge, right? Does the series converge to a finite sum? You look at this sequence and you see what is happening, right? So we look at this sequence and we decide if this sequence converges. Do the partial sums get closer and closer to a particular number? If they do, we're going to call that number S the sum, and we'll say that that's the sum of the infinite series. And so we'll do an example to talk about what that means. Okay? So here's an example. This is everybody's favorite example. It will be your favorite example too. So it's in sigma notation. Don't let that freak you out. I'm sure you remember sigma notation. So this one starts with I equals 0. So if I equals 0 and then you plug that in, so that's 1/2 to the 0. And then I is 1, I is 2, I is 3. So when I is 1, this is a half. When I is 2, I is 3, I is 4, etc., etc. So we have powers of 2 on the bottom. So let's look at the partial sums. First partial sum is the first term. Second partial sum is the first two terms, 1/2. The third partial sum is the first three terms. I did the math for you. It's 1 3/4. The fourth partial sum is the sum of the first four terms. So it's what I had before plus another eighth. So 3/4 plus an eighth is what, 1 7/8. The fifth partial sum is all those plus one more plus 1/16. So that's going to be 1 7/8 plus a 16th, which gives me this. You can pause and check that if that arithmetic was too fast for you. And then the question is, what's happening here? So if I add up 1 term, 2 terms, 3 terms, 4 terms, 5 terms, this is what the sum is. What's the trend? Are these partial sums getting closer and closer and closer to a number? You might say they're getting bigger. Well, in fact, they are getting bigger. But the question is, are they bounded, right? Is there a limit to them? Is there a number that they will get closer and closer to but not go over? And in fact, there is. These numbers are getting closer and closer to, do you know, do you know, do you know? They're getting closer to 2. Okay. So is this sequence converging? Yes. What is it converging to? It's converging to 2. And so we say that that's the sum of the infinite series. And so we the math people, are very comfortable saying, right, that this sum, which includes an infinite number of terms, actually adds up to 2. All right? And that's how we find, and how you also will find, the sum of an infinite series. This wasn't much of a proof. I just sort of said, look, they're getting closer to 2. If you wanted to do a proof, you'd have to make a formula for this. It's not that hard. And then show that that goes to 2. Instead of doing that proof, let's do another example. So with this one, here the sigma starts at I equals 1. So 1 over 1, 1 over 2, 1 over 3, 1 over 4. It's the harmonic series. What are these partial sums look like? So here's the first term, the first 2 terms, the first 3 terms. I gave you some decimal. The first 4 terms, the first 5 terms. So these partial sums are also getting larger and larger and larger, like the last one. But the question is it bounded? Okay? Is there a limit? Is there a number that these never go over? Perhaps these will never get larger than 2.5. How do you know? It's kind of hard to make a formula for this one, actually. I don't really know a formula for the sum of the reciprocals, which is a lie. I probably do. But most people don't, and that's okay. So what do you do? All right, I don't know, which is not true. I do know. So in this particular case, I'm going to tell you with my special calculus knowledge that this particular sequence of partial sums is unbounded. So it does get larger than 2.5. In fact, I used a computer and I said, will the partial sums ever get larger than 10? And yes, it takes 13,000 terms. But if you add up 13,000 terms, this will eventually add up to something larger than 10. And in fact, if you pick another number like 20, it'll eventually be larger than that. And so this series diverges. The partial sums are unbounded. They do not get closer to one finite number. And this is going to be one of our primary goals in this unit, is to say, does a particular infinite series converge or diverge? So we'll talk more about that.